In this video, we are going to look at example 18.7 from the textbook. This is our first timber column analysis problem. And so we are asked to find the allowable axial compressive load for a pin-pin connected column. So the top support is a pin, the bottom support is a pin, and that tells us that our K value is 1.0. It's an 8 by 10 column. As I said in the last video, using a rectangular column is not the most efficient choice. The 8 by 10 versus an 8 by 8 gives us a slightly bigger area, so it does increase the capacity a little bit, but we're still limited by the 8-inch dimension when it comes to stability, and so it doesn't really gain us very much additional strength. But nonetheless, that's what has been chosen, perhaps for some architectural reasons. We've got an 8 by 10, and it's S4S. That just means it's been surfaced on all four sides, so we can use the S4S dimensions in the back of the book. And it's made up of Douglas fir. That's going to affect the allowable stresses and the modulus of elasticity. The unbraced length of it is 10 feet, except it's generally preferable when doing column design to use inches. So 10 times 12 is 120 inches is our unbraced length. So the first thing we need to do in any timber column design is make sure that our effective length divided by D is less than or equal to 50. If it exceeds 50, then it means that this column is too slender and is not permitted. So what is our unbraced length, or effective length, I should say? The K times L over D is equal to 1.0 because it's a pinned column, and L is 120. How about D? So although it says 8 by 10, an 8 by 10 is not really 8 by 10. We should look up in appendix, let me check what appendix that is. In appendix E, we can see the dressed sizes of our columns, which are the actual sizes, not the nominal sizes. So an 8 by 10 is actually where did it go? There it is. 7.5 by 9.5. At least according to our textbook it is. So the D, the least dimension, cross-sectional dimension, is 7.5. So we need to make sure that this is less than 50, and it is equal to 16, which is actually much less than 50. So it is okay. Now we need to go to appendix F in the textbook and look up some values for Douglas fir. So from appendix F for Douglas fir, let's see what we've got here. We've got F sub C, which is the allowable compressive stress parallel to the grain for Douglas fir, is 1050 psi. That's a slight difference from steel. Most of our stresses when we deal with steel are in KSI, and typically when we deal with wood, we are working with PSI. And that's because timber is significantly less strong than steel. They have similar strength-to-weight ratios, but wood is a lot lighter weight, and it therefore carries lighter loads. And so 1050 psi is the allowable stress parallel to the grain. And the modulus of elasticity is 1700 KSI. Now, I don't know why the book tends to do this. It mixes the units in the appendix here. I would prefer to just stick with PSI. So that's going to make 3 additional zeros on the end of this by converting from KSI to PSI. So it's actually 1.7 million PSI is the modulus of elasticity. That's just my preference, is to stick with consistent units throughout the problem. Okay. To begin our analysis, we are going to, what I like to do is I like to first find the alpha value. The alpha value is going to go into the CP formula. The CP formula is then used to determine our allowable stress. So let's just start with alpha. Alpha is equal to 0.3 E divided by LE over D squared times F sub C. So that is 0.3 times the modulus of elasticity is 1.7 million, 1,700,000 PSI, divided by LE over D, we have already calculated, it's 16. So this is 16 squared. And F sub C we looked up is 1,050 PSI. So you do need to make sure that these units agree with each other. If we had used KSI in the numerator, we'd have to convert the allowable stress to KSI as well. So let's calculate that. I'm getting 1.897 as our alpha value. So this can now be used in the CP formula, the stability adjustment factor. This is going to be 1 plus alpha divided by 1.6 minus the square root of 1 plus alpha divided by 1.6 squared minus alpha over 0.8. So what I like to do is this 1 plus alpha, that can easily be done in your head, basically, right? 1 plus alpha is going to be equal to 2.897. So when I write these variables into the formula, I just go ahead and do that particular computation mentally and just write it down. So 2.897 divided by 1.6. The reason I like to do that is because then if I'm punching into my calculator, I don't need to worry about putting the numerator inside of parentheses. I just have a single term in the numerator. So it simplifies the calculator work a little bit. And so again, I've got in the numerator here, I've got 1 plus alpha, so that's 2.897 divided by 1.6. And then that's going to get squared. Minus, now I have noticed some students in the past following my advice here, using the writing in the 1 plus alpha value here, and then they kind of, their mind must wander, and then in this last term they write 2.897 again. But in this last term in the formula, it's not 1 plus alpha, it's just alpha. So 1.897, so be careful of that, divided by 0.8. So again, if you're comfortable with your calculator skills and you feel like you could punch this all into your calculator and in one step hit the equal button and get a single answer, that's great. But this is one of the areas where I see students struggling. They have the equation set up correctly, but then they get the wrong answer because they didn't key it into their calculator properly. So there's nothing wrong at all with breaking it down into smaller chunks. Let's just do this part first. 2.897 divided by 1.6, and I get 1.81. And then I'm going to subtract the square root of, let's look at this term next. Let's solve that. 2.897 divided by 1.6 equals, and then square that answer, and I get 3.278. And then subtract the last term, 1.897 divided by 0.8. 2.371. Okay, so now let's look inside our radical. 3.278 minus 2.371 equals 0.907. So it's going to be square root of 0.907, 1.81 minus that. So now, I think that's simple enough. I can just put the whole thing into the calculator. 1.81 minus the square root of 0.907, and that gives me 0.858 is our CP value. So solving this equation piecewise isn't strictly required, but it is my recommendation, especially if you find that you're having trouble. You get the equation set up right, but then you punch it in your calculator and something just doesn't come out right. Just break it down into smaller chunks. That's fine. So what this is telling us now is that our allowable stress for this column is going to be equal to the F sub C, the allowable stress from the appendix, multiplied by CP, the stability adjustment factor. F sub C, the allowable stress parallel to the grain from the appendix for a Douglas fir, was 1,050. So that's 1050 psi. And essentially what this stability adjustment factor is telling us is that because of the slenderness of this column, because of its height versus its width, we really can only rely on about 86% of this allowable stress when we design the column. If the column was shorter, C sub P would be bigger. If the column is taller and more slender, then this stability adjustment factor gets less. So 1050 multiplied by 0.858 is equal to about 901. I'm getting 900.9. So I'm just going to say 901 psi is the allowable stress. Okay, so stress times area will give me the allowable load. So the load allowable is equal to that stress allowable multiplied by A. So I've got 901 psi, and I've got an 8 by 10, but the area of an 8 by 10 is not just 8 times 10 or 80. I would recommend looking it up in the appendix. So looking up an 8 by 10 in the appendix of our book shows that we have an area of 71.3 square inches. And so that gives us an allowable load of 64,200, if I round that to 3 significant figures. And that would be in pounds. So that would be 64.2 kips. Okay, so that is how we do timber column analysis. In the next video, we'll look at timber column design.